All right, everyone. Thanks for coming for my talk. My name is Tunji. I'm from Snowflake. I'll be talking on DeepSpeed. So what is DeepSpeed? It's an optimization library for making large distributed training efficient, easy, and effective. And by that, I mean that if you use DeepSpeed for your training workload, whether you're training on a single GPU or up to 100,000 GPUs, you would have sustained high efficiency or high performance. And DeepSpeed is easy to use. It runs out of the box. You should download and you get running pretty quickly. And it also democratizes AI by basically reducing the GPU budget for you to either build state-of-the-art AI or to use state-of-the-art AI. And DeepSpeed became a part of the PyTorch Foundation earlier this year. So DeepSpeed was motivated, like when we created it, was motivated by the observation that scaling is what drives state-of-the-art in deep learning. And here I'm showing two interesting dimensions of scaling. On the y-axis is the model size, and on the x-axis is showing the training data size. And as you can see, from 2018 till now, on both dimensions, we've seen 3 orders of magnitude of scaling on both sides, on both dimensions. And that has created significant system scalability challenges in our modern computing systems. And so the first problem we tackled in the DeepSpeed project was that of the GPU memory wall. And so this is what sort of restricts the ability to scale the model, because then the model can no longer fit in the memory of a single GPU. And to address this problem, we created 2 directions of optimizations. The first direction is something we call zero. So zero is a memory optimization that would partition your model across multiple GPUs on the data parallel rank. And in addition, could also offload the model states onto CPU or NVMe. And so this combination essentially means you can scale your model almost infinitely, right? The second direction of optimizations is what we call 3D parallelism. This allows you to combine things like tensor parallelism and pipeline parallelism with zero. And so basically your ability to scale your model is pretty much infinite. The consequence of these 2 directions is that we effectively solve the GPU memory wall, at least as far as the model scaling was concerned. So for example, as far back as 2021, we had provided system support for trillion parameter scaling. We already had that available, even though the models of that scale did not exist back then. And the other impact was that this technique is so effective, it's really been adopted by other scaling frameworks that are out there. Going forward, the new things that we're looking at in DeepSpeed now, there are other scalability challenges, and I'm going to talk about a few of them today. But broadly, the ones we're looking at today fall into offloading. So this is an important democratization technique because this allows us to reduce the GPU budget by basically utilizing CPU and NVMe, right? Long context, our context windows are also scaling very dramatically as more applications are being digitized with AI. We're also taking advantage of compilers technology, and we have checkpointing becomes more complicated once you start doing distributed training, and I/O itself also becomes an important scalability problem. The rest of this talk, I'll focus on just the first 3 lines of work. So the first work that I'll talk about in offloading is something we call SuperOffload. It's one of our newest work. This is making offloading efficient for the emerging superchip architecture. So the motivation here is that superchip are new. I mean, they're just sort of becoming available broadly, but there hasn't been a lot of studies about how to efficiently use them for large language model training. And in particular, existing offloading techniques were designed for the PCIe or loosely coupled architectures, right? Whereas the superchip is a different architecture where the CPU and the GPU are closely coupled and have a much faster interconnect between them called the NVLink C2C. And so this means that if you use existing offloading technologies, you're basically inefficient. You underutilize the capabilities of your superchip. And so to address that, we created a number of optimizations that leverage the hardware features of the superchip. And in particular, we have a technique called speculation then validate, and I'll talk about that. We're able to to split the optimization computation over both the GPU and the CPU, whereas traditional approaches would have run the optimization computation just on the CPU. We have a superchip aware casting, so in mixed precision, often you have to typecast. We've designed optimizations that is optimal for the superchip architecture, and part of that too is that we've implemented an Atom optimizer that runs efficiently on the Grace CPU. This work will appear at ASP+ next year, but the key takeaways, the high-level results we got is that we are able to fine-tune large models like the GPT-OS 20B or the Qwen 40B on a single GH200, the Llama 70B on 4 GH200, and in all of these cases, we're able to hit over 50% of the MFU, over 600 teraflops. So the first technique is what we call the speculation then validation. So here, showing basically the flow, the top picture there is showing how the traditional offloading approach works. So there you have your forward pass, right, and then you have your backward pass, all of which are taking place on the GPU. At this time, your CPU is idle, and then we copy the gradients onto the CPU in order to do the GPU, to do the optimizer computation on the CPU. So while that is going on the CPU, that means your GPU is essentially idle, right? This is a huge waste. Now, the reason we need to do this is that we typically need to see all of the gradients, one, to detect if there are any kind of denormalized values, underflows, overflows, right, before we can move to the optimizer computation. So that's one reason we wait for all of the backward pass to complete. Another reason is we often have to do gradient clipping, and such clipping is based on global norm information. So this is why the traditional approach basically serialized the backward pass and the optimizer computation. But what we did in SuperOffload is basically we found a way to overlap them in a speculative manner. So we start doing the optimizer computation as soon as gradients are available in a speculative way. And we still check for those conditions, those global conditions that I talked about, and we would do a rollback if it turns out that something went wrong. And by doing this, we're able to keep both the GPU and the CPU constantly busy. We are able to do some of the optimizer computation on the GPU as well, which also provides additional acceleration. Now, doing this, if rollbacks were frequent, then this would not be a win, right? But we take advantage of the fact that when you're training, typically this conditions that could cause a rollback, such as overflow, underflow, or clipping, they don't happen often throughout your entire run. They happen at the very beginning of training and towards the end of training. And the plot here I'm showing is for the Bloom 176B model, which shows that over the training time, 80,000 steps, that the conditions for doing a rollback occur less than 1% of the time. So it's really not a performance overhead. The other optimization I want to talk about is the casting. So like I said, with mixed precision training, your forward backward is in low precision. Your optimizer computation is in high precision. All of this is for numerical stability. Now, this means you have to cast your gradients and parameters as you switch from your CPU to the GPU. In the old approach, we typically try to minimize the volume of things we transfer. So usually you would do the casting on the GPU and try to only transfer in low precision, right? But by studying the C2C, the Grace Hopper, the GH200, we observed that the right approach actually is to always cast on the GPU, right? So and it's very fast. And because the C2C connection, which is 450 gigabytes each way, is so fast, the fact that we're doubling the communication volume really doesn't matter. And so that's sort of what we're showing here, where the option of trying to minimize the communication volume is not so important in the Grace Hopper architecture. Then the other part shown on the right-hand side is our Atom optimizer implemented in the Grace CPU. And we take advantage of all of the vectorization features that are available, vector units that are available in the Grace CPU. And this allows us to get, Atom optimizer that's 3 times faster than the PyTorch. And we believe this is the first open source Atom implementation for the Grace CPU, and we're pretty excited about that. So all in all, for SuperOffload, we get speed ups compared to the baseline of about 4 to 5x speed up. The technique itself is composable with existing, Zero and Ulysses techniques, and so that means you can plug it in easily into your existing workflow. All right, let me move on to the next talk, ZenFlow. So this is another offloading optimization that we created in collaboration with our academia partners. So the problem that ZenFlow tries to solve is similar, but it's solving it on existing hardware. Which is basically that when you're doing the optimizer computation on the CPU, your training basically stalls, right? And that's kind of showing that here. The first figure on the left is showing that, yes, offloading helps you to scale your model size compared to no offload, but then when you start to do your GPU then ends up being idled a lot when you're doing optimizer computation. And given that the speed of the GPU and the CPU continue to grow, the speed gap continues to grow, it means that this stalling is only going to get worse with time, right? So what can you do? So plot is just showing sort of some actual numbers where your forward pass takes about 45 milliseconds, your backward pass takes 2,000 milliseconds. A big chunk of that comes from the fact that you're offloading the gradients to your CPU, and then you look at the CPU time for the parameter update. It's about 4.6 seconds. It's just really a big bottleneck. This makes it hard to overlap, right? If you have this sort of numbers, you can't really overlap. But then one observation we made is that in the pre-training scenario, in the post-training scenario and fine-tuning, that not all the gradients are created equal. Only a few of the gradients are actually very critical to your convergence. And this is the plot we're showing here. And the main takeaway is that only 1% of your gradients are responsible for about 90% of the total norm of gradients. And what that means is that we can essentially take those 1% of the gradients, run them on the GPU, and while the others that are not so important, we run them on the CPU, but we don't even update the parameters frequently, right? So there's a delay. We can afford to delay the updates there because the norms are just pretty much insignificant at this point. And that's essentially what we do in ZenFlow, right? So we come up with an asynchronous update where certain gradients get updated every iteration, while some get updated, sort of in a slower fashion, if I might put it that way. And this helps, and the benefits is now the 1% of gradients can be updated on the GPU because they're so small, it doesn't really affect your model scale size. And then the slow ones get updated on the CPU, and and that can be done sort of lazily. And the consequence of that is that if we compare to the baseline and looking at, I guess one thing that's really interesting is that it doesn't affect the accuracy. And actually, in one of the benchmarks, we saw a higher accuracy compared to, the sequential approach. But overall, it improves your speeds by about 5x speed up compared to the baseline. The next work I'd like to talk about is what we call the Arctic long sequence training. This is from our Snowflake AI research. And the motivation for this work is that the context window for your models is growing. So if you think back to 2018 when we had BERT, the context window for that was about 512 tokens. Since then, the largest one that I've seen recently, and the last time I checked, was about 100 million tokens. So the context windows are scaling, growing really, really fast. And so then the challenge is how do we train models that have long context capabilities? And that's what we've done in Arctic sequence, in ALST or Arctic long sequence training. So to drill down to what is the cost or what challenge does the longer sequence create? Here I'm showing the memory costs of scaling up your context window, and here I'm using just the 8 billion Llama 3 model. Here I'm plotting the activation memory as you increase the context length on the x-axis. Y-axis is showing the memory usage. I have gradient activation enabled already here, so it's not much else we can do. And as you can see, the model, the context, and this is just the activation memory, so we're ignoring the model memory here. You can see that it just scales linearly. And what this really means is that on a single GPU, the memory wall shows up again. It turns out we can't support more than 32,000 context window, more than 32,000 tokens. So that's a problem. And there are multi-GPU solutions that try to parallelize the context window across multiple GPUs. But those are not general. They don't work very well. One, they don't support Hugging Face fine-tuning, which is really the primary way most people do fine-tuning these days, right? You grab your model from Hugging Face. And so this is a significant adoption barrier. And secondly, they don't support the more modern attention. So it works well with multi-head attention, but not something like group query attention or MQA. And so to address that, we created Arctic long sequence training. And so the key points there is a suite of optimizations for helping you to scale your context window. And there are three directions of optimizations here. One is tiling. So we end up doing the tile computation. Then we also leverage parallelism. We're able to parallelize your context across GPUs. And we take advantage of the newest memory optimizations in the latest versions of PyTorch. So by solving this problem, we're able to, and we also provide the Hugging Face fine-tuning capability and support for the newer attention mechanisms. And so here I'm just sort of showing that with all of these techniques on a single GPU, we've been able to increase your context window from 32K to 500,000 tokens. And you can also see that as we add more GPUs, we're actually linearly scaling your context window. So let me talk a little bit about the optimizations here, just briefly. So the first one is the sequence tiling. Now, tiling is a pretty standard computer science concept, right? Where if you try to break your problem down to reduce the footprint. And so it turns out with your attention, there are actually some operations where the intermediate tensors are a function of your context length. And so examples of that would be your logits or your loss computation. And so the solution here is basically instead of trying to compute on all of it at once, compute on tiles of your sequence, and that helps to reduce the size of the intermediate tensors. I'll point out that this only applies to operations that do not have cross dependencies. So like your causal attention will not be suitable for this optimization. But there are other parts of the loss and logits, like I mentioned, or the embeddings that would actually work well with this. And here, I'm basically just showing that for the loss computation in an 8B model, with and without tiling. On the left-hand side is no tiling. On the right-hand side is with tiling. And this is a PyTorch memory profile. It shows the reduction in not only in the memory, but also in the peak memory. Sequence parallelism, we build on the Ulysses, which already does parallelism, parallelize your context over multiple GPUs. And here the challenge with Ulysses is that it only assumes MHA, multi-head attention. It's not able to support the newer attention mechanisms. And so we're able to support that by basically replicating the KV, right? So the challenge is that we're trying these optimizations of GQA, MQA are trying to reduce the memory costs of your attention. And in Arctic long sequence, we're able to support that by basically replicating the KV. All right. Results here are just showing that on a single GPU, we can scale your context by 16x, and we achieve a linear context scaling. All right, I'll move on in the interest of time. The last work I'll talk about is the compiler work called DeepCompile. Now, the motivation for this is there are a lot of parallelism techniques that are out there, and integrating them into your workflow is actually non-trivial. So you have tensor parallel, pipeline parallel, expert parallel, all of this, integrating them into your workflow is actually challenging. And then additionally, tuning them for performance is also even more challenging, right, if you try to do it manually. And so the approach we've taken is we've decided to automate this using compilers, compiler technology. So the compiler will go in and transform your single GPU model into a distributed model. And the compiler will also, at runtime, learn things to profile your model and your training run and then re-optimize for it. And yeah, I'll just show some of the results we have. So the 0 stage 3 is a very popular parallelism technique. And with DeepCompile, we're able to automatically take your model and apply 0.3 to it as a compiler pass. But more interestingly, what I'm showing here is that we are also able to do things like prefetch much more smartly. By looking at how much memory is available at different regions of your training, we're able to prefetch aggressively when you have a lot of memory and also scale back when you don't have much. This is very hard to do manually. But with a profile-guided optimization, we can study your model and actually apply these optimizations. The result is that compared to manual parallelism, we can see up to a 50% speed up for 0.3. We've also applied this to 0 stage 1 and to just offloading, and we're seeing really good speed ups by just using the compiler approach. We also applied this to reinforcement learning, in particular to the training portion of reinforcement learning. And so here we're comparing, a baseline of the manually implemented 0.3 with flash attention and then the compiler approach. And so on the forward pass, we're able to cut the forward time in half, and while on the backward pass, we're able to get like a 60% improvement. So just to wrap up, I think I have, and have some time for questions. So like I said earlier, DeepSpeed is an open source project. Its growth and its advancement is really based on the open source community. And so here I'm just kind of showing like the contributor lists is, we have over 400 contributors. It's heavily used by the open source community. We've constantly been trying to keep up with releases in response not only to the innovations we're integrating in, but in response to requests from users. We're under the PyTorch Foundation. We've recently constituted a steering committee made up of all of the companies I've listed here. And I'm hoping this is a call to you. If this line of work is something that's interesting to you, we would love for you to join us. Our goal is to make state-of-the-art AI available and free for all, and we think we can do that. We have a good track record, and we're just really relying on the community to help us out here. That's all I have. Thank you. With PyTorch, you mean? You mean merge with PyTorch? Yeah, that's a great question. I think we don't need to merge with PyTorch, because if you sort of look at the trajectory of how both projects have evolved, PyTorch we are sort of more, I'll say, cutting edge in the sense that we try out ideas that are maybe risky, and it takes a while for those ideas to demonstrate whether they will really pan out well or not. And so we have we break more often than PyTorch will break, if you understand what I mean. But the good news is we do have some technologies like Zero, for example, that we created and now is part of PyTorch, like as FSDP. Universal checkpointing, which I didn't talk about today, was something we created, and it turned out to be very useful and is now part of native PyTorch. So I kind of view us as the guys who are running ahead, trying out the crazy, daring ideas, and some of them will pan out well, some won't, but all in all, we're helping people, we're helping push that frontier. And I think PyTorch's quality requirements cannot allow it to do that, right? Like, PyTorch cannot break as often as we break, just, so, yeah. Yes. Yes, I believe it's architectural agnostic, yes. It's just based on the touch compile graph. It's really just based on touch.compile. So, and we run on top of PyTorch, right? So we're really a PyTorch on top of PyTorch. So, and we follow their APIs and all that, so, yeah. Yeah, thank you. Any other question? Yes, sir.
I'm interested in the speculative parallelism that you had in the first slide deck.
Yeah.
Are there any characteristics or information that the speculative parallelizer used to help it make good decisions?
In what sense? Like, can you say a little bit more?
So if we're speculating on work items being parallel, there are probably characteristics about those work items we might use to make a good decision, like, oh, these are probably parallel, or oh, that's definitely not.
Right, right, yeah. Okay, it's very domain specific. We know that the gradients that are created on the backward pass are what's used for updating the parameters. But we know that individual parameters can be updated independently of all the other parameters, right? Because their gradients are different. And so that's what we're leveraging. The fact that individual parameters have individual gradients and they're updated by only their gradients, not some global information. That's what we're, yeah, right. Okay, thank you.